welcome to the deep dive. Today we're digging into something called DeepSeek-OCR. Now, you hear OCR, you might think, okay, text recognition, useful, maybe a bit niche.
Yeah, but that's sort of missing the bigger picture here. The core concept they're pushing, Contexts Optical Compression, or COC, it's actually trying to redefine efficiency for large language models.
Okay, so it's not just about reading text off a page.
Not at all. It's about tackling this massive computational bottleneck LLMs have, especially with, really long texts.
Right, the problem where if you feed in, say, a 10,000 token article.
Exactly. The model has to chew through that whole sequence, token by token. That's 10,000 separate steps. Each one costs FLOPs, memory, time. It's just inefficient.
It feels like forcing this super smart AI to read like a first grader, sounding out every single letter, even though most text tokens are like really low information density for a machine.
That's a great way to put it. So DeepSeek's whole idea is, look, stop making the model read it in that slow, sequential way.
Let it see it instead.
Precisely. Use the visual information, the pixels, the layout, the fonts, all of it as a kind of dense compression channel.
Ah, okay, so that's the optical compression part. You're squeezing the meaning into the visual representation.
Yeah. Instead of that long, sparse string of, say, 10,000 text tokens, you convert the document into maybe, I don't know, a few hundred really dense visual tokens.
And these visual tokens pack more punches.
Way more. They don't just capture the letters and words, but also the where, the formatting, the spatial relationships between things on the page. You get the same, or arguably better, semantic understanding.
But with maybe, 10 times fewer computation steps?
Exactly, an order of magnitude fewer steps. And that directly cuts down computation time and memory usage. It's a huge potential win.
It's interesting, you see people like Andre Karpathy asking this bigger question now. Are pixels actually a fundamentally better way to feed information into LLMs than just plain text?
It definitely makes you wonder, doesn't it? If seeing the information is just that much more efficient, then maybe our whole reliance on purely text-based sequences is, well, maybe a bit outdated, like technical debt we've built up.
So how does this DeepSeek-OCR actually work? What's under the hood? You mentioned a dual-brain system.
Right. It's what they call a unified end-to-end vision language model, or VLM. Think of it as two main parts working together: the deep encoder and the DeepSeek 3B-Mo decoder.
Okay, let's break that down. The deep encoder first, that's the compression part, right? The optical part.
That's the one. It's about 380 million parameters, and its whole job is to take these high-resolution images and process them efficiently.
And they built it by combining existing parts, like a Frankenstein model.
Sort of, but in a smart way. Think of it like hiring specialists. They took Meta's SAM-based model, that's about 80 million parameters, which is really good at local perception, like focusing on details using something called window attention.
Okay, so that's the detail expert.
Yeah. And then they paired it with OpenAI's CLIP large model that's much bigger, 300 million parameters, which provides the dense global attention. It understands the whole picture and brings in, a lot of general world knowledge.
But hang on, if you just feed a huge image directly into CLIP, wouldn't that still be incredibly computationally expensive?
Absolutely. That's where the real magic happens. The key component is this thing called the 16x token compressor that sits between SAM and CLIP.
A compressor. Okay, so it shrinks the data before the big CLIP model sees it.
Exactly. Think about a standard 2024 by 1024 pixel image. Initially, that might get broken down into, say, 4,096 small patches or patch tokens.
Right.
The 16x compressor looks at those 4,096 tokens and aggressively squishes them down to just 256 vision tokens.
Wow, okay. So from over 4,000 down to 256, that's a massive reduction before the heavy lifting of the global attention model even starts.
That's the core of the efficiency gain right there. It dramatically cuts the input size for the most computationally demanding part.
Got it. So the deep encoder compresses the visual info into these dense tokens. What happens next, the second brain?
Right. Those 256 dense visual tokens then get passed to the DeepSeek 3B-Mo decoder. This is the language brain. Its job is to take that compressed visual representation and translate it back into structured text or whatever output format you need.
And the MOE part stands for mixture of experts. That's another efficiency trick, isn't it?
It is, yeah. It's a clever design. On paper, it's a 3 billion parameter decoder, which gives it a lot of expressive power, a lot of capability.
But you don't actually run all 3 billion parameters every single time.
No, that's the beauty of MOE. When it gets a task, like transcribing a document page, it only activates a small subset of its experts. In this case, it uses just 6 specialized experts out of 64 available, plus 2 shared experts that are always active.
So the actual compute cost during inference is much lower.
Much lower. You get the power of a 3 billion parameter model, but the inference cost is closer to a model with only around 570 million active parameters.
That's really efficient. It's like having a huge toolbox, but only pulling out the exact tools you need for the job at hand.
That's a perfect analogy. High potential capability, but low running costs. And another practical thing is the flexibility in how much compression you apply.
The different modes.
Right. You can choose based on the document. There's a tiny mode 520 by 520 resolution that gives you just about 64 vision tokens, maybe good for like a quick scan of a receipt or something simple.
Then the standard one.
That's base mode, 1024 by 1024 resolution, which gives you the 256 tokens we talked about, probably the default for good quality.
And then there was that Gundam mode. Sounds intense.
Yeah. That's for the really tough stuff. Ultra-high resolution documents, think complex academic papers, dense financial reports, maybe a full newspaper page with multiple columns and images.
So how does that work? Just a massive image?
It uses dynamic resolution. It basically tiles the document, processing multiple high-res sections, maybe like 640 by 640 chunks, plus one overall lower-res view.
Okay, so it can zoom in on details while keeping the overall context.
Exactly. It preserves the fine detail needed for really complex layouts. Now, this might push the token count up maybe to around 800 vision tokens for a really dense page.
But even 800 visual tokens is still likely way, way less than the thousands of text tokens you'd need to represent that same page traditionally, right?
Oh, absolutely. The compression factor is still huge.
So let's talk numbers. How well does this compression actually work in practice? What's the accuracy like?
The results they shared are pretty compelling. They found that DeepSeek-OCR hits around 97% accuracy, even with a 10x compression ratio.
10 times compression. So swapping 10 text tokens for one vision token, roughly, and still getting 97% accuracy. That's impressive.
It really is. And even when they pushed it harder to a 20x compression ratio, it still maintains something like 60% accuracy.
Which kind of proves the point, doesn't it? That the visual representation is just a much denser, more efficient way to hold the information for this kind of task.
Definitely. And you see this reflected in benchmarks, too. On a test suite called OmniDocBench, DeepSeek-OCR apparently outperformed leading models while using significantly fewer tokens.
Like compared to what?
Well, for instance, they mention it beating a model called GAOT OCR 2.0. GAOT needed 256 tokens, but DeepSeek-OCR in its small mode achieved better results using only 100 vision tokens.
Okay, less than half the tokens for better performance.
And then there's a comparison with another system, MinerU 2.0. Now, MinerU apparently needs over 6,000 text tokens per page to do its work.
6,000. Wow.
Yeah. DeepSeek-OCR, even in that complex Gundam mode for dense pages, was using fewer than 800 vision tokens and still outperforming MinerU.
That's not just an incremental improvement. That's a different league of efficiency.
It really shifts the scale. And this efficiency isn't just theoretical, it translates to serious throughput. They estimate a single A100 GPU, the 40 GB version, can process over 200,000 pages per day.
200,000 pages a day on one GPU.
Which makes it practical for really large-scale document processing tasks.
You can imagine companies digitizing huge archives, or even generating training data.
Exactly. Scale it up. They calculated that with just 20 servers, each loaded with 8 A100s, you could potentially process something like 33 million pages daily.
That's game-changing for creating the vast data sets needed to train the next generation of AI models, both LLMs and these VLMs.
It solves a major bottleneck in the AI development pipeline, getting enough high-quality, structured data quickly and affordably.
And it's not just about getting the text out, right? You mentioned it understands structure because it was trained on something called OCR 2.0 data.
Right. That training gives it deep parsing capabilities. It goes beyond just a flat text transcription. It understands things like headings, lists, tables.
So it can look at a financial chart in a report.
And potentially convert it directly into structured data, like an HTML table or a JSON object. That saves a ton of manual effort or post-processing work needed for things like automated financial analysis.
That's huge.
It can even handle specialized stuff, like recognizing chemical formulas in scientific papers and outputting them in standard formats like smiles. And it apparently works across almost 100 languages.
That structural understanding and efficiency, it loops back to what you said earlier about long context LLMs, doesn't it?
It really does. If you can reliably take, say, a 6,000 token document page and represent its core meaning with just 800 visual tokens, you fundamentally change the economics of context length.
Because the compute cost doesn't explode quite so dramatically as you add more and more information.
Exactly. It suggests a path towards LLMs that could handle vastly longer contexts, maybe theoretically unlimited, because the token count representing that context isn't growing linearly with the raw text volume anymore.
This feels like it connects to some really interesting ideas, almost borrowing from neuroscience. They talked about visual forgetting.
Yeah, that's a fascinating concept they introduced, inspired by how human memory seems to work.
I s-
Well, think about your own memory. Something that happened yesterday is probably pretty sharp, lots of detail, but a memory from 5 years ago. It's likely fuzzier, right? You remember the gist, the key points, but maybe not the exact wording or the precise layout of the room.
Okay, yeah, the details fade over time.
DeepSeek-OCR can simulate something like that. Imagine you have a long-running conversation with an AI, or you're feeding it a massive document history.
Hmm.
The model could store the most recent information at high resolution using, say, the standard 256 vision tokens per chunk, sharp and detailed.
But the older stuff,
The older context documents from weeks ago, conversation turns from hours ago, could be progressively downsampled, stored at lower resolutions, maybe using the tiny mode 64 tokens, or even fewer.
so the older information becomes visually blurrier, consuming fewer resources, but hopefully retaining the essential meaning.
Exactly. It's like the AI maintains the gist of the past without the massive computational overhead of storing every single detail perfectly forever. It's a potential mechanism for managing extremely long histories efficiently.
It's like enabling a form of selective memory for the AI.
Pretty much. A computationally efficient memory decay.
Okay, so bring this back to practical use today. There seems to be a bit of a debate, or at least different perspectives, when you compare something like DeepSeek-OCR to more traditional, maybe specialized OCR tools, especially for businesses.
There definitely is. On the one hand, the big advantage users point to is the structural recognition we talked about.
Right, getting clean tables, headings, lists.
Yeah. People using the open source DeepSeek model report, it's much better at that than older systems like, say, Tesseract. You get output that's closer to clean markdown, which saves a lot of time on cleanup and post-processing. That's a tangible saving.
Okay, so that's the pro argument, better structure,
Yeah.
potentially less manual fixing. What's the con?
The con, or maybe the caution, comes from the fact that DeepSeek OCR, particularly the underlying VLM, is fundamentally a large language model.
And LLMs can be unpredictable.
Exactly. They are non-deterministic. A specialized, rule-based OCR system, or even some AI OCR tools designed for specific tasks like invoice processing, aim for consistency, they'll read $1,234.56 the same way every single time.
But an LLM might not.
It might not, because it's probabilistic. There's always a chance, however small, of inconsistency. It might drop formatting, misinterpret something slightly, or worse, hallucinate.
Hallucinate, like making up text that wasn't there.
Or subtly altering critical data. The example often cited is changing that $1,234.56 to just $100, by dropping the punctuation, or maybe changing a date or an invoice number.
Which, for business-critical documents like invoices, legal contracts, compliance forms, that's a massive risk.
It's a deal breaker for many regulated industries or high-stakes financial processes, so the tension is between the advanced structural understanding and potential efficiency of the VLM approach versus the reliability and determinism needed for certain business tasks.
So it's a trade-off between sophistication and predictable accuracy.
That seems to be the crux of it right now. For generating training data or maybe less critical document analysis, the VLM approach is incredibly powerful. For high-stakes, auditable processes, specialized tools might still be preferred for their reliability.
Stepping back, though, the big takeaway for me isn't just about whether DeepSeek OCR is the best tool for invoices today. It feels like the real breakthrough is the validation of that core principle.
The Context Optical Compression.
Yeah. Proving that the visual modality, treating the document as an image, can be a fundamentally more efficient container for information than just a linear sequence of text tokens.
I agree. It's a powerful proof of concept. It strongly suggests that future gains in AI efficiency, especially for handling vast amounts of information, might come from smarter ways of representing and compressing data, likely leveraging multiple modalities like vision.
Decoupling context length from just adding more and more text tokens seems key.
Absolutely. It's about finding denser ways to represent knowledge.
So as we wrap up, Thinking about this idea of limitless context enabled by optical compression and this concept of visual forgetting, letting the AI compress or blur older information to save resources. It
Mm.
leaves us with a pretty provocative thought, doesn't it?
What's that?
If our AI systems need to forget or compress the details of the past to achieve this limitless memory, how much detail are we actually comfortable letting them lose? Where's the line between efficient summarization and unacceptable information loss, especially if we rely on these systems for long-term knowledge retention?